In this lecture, we are going to discuss another theorem from the chapter of quadrilaterals. This theorem is called as the midpoint theorem for the triangles. However, it's in the chapter of quadrilaterals because some concepts related to quadrilaterals and parallelograms are utilized in proving this particular theorem. Okay, it's called as the midpoint theorem, and what it states is that we'll first talk about the construction and some observations that are made with regards to a triangle, and then we'll formally state the theorem and prove it, and also then state the converse of the theorem and also prove the converse of the theorem. Okay, so if we have a triangle ABC, and if we have E as the midpoint of the side AB and F as the midpoint of the side AC, and if we join these 2 points EF by a line segment, the following observations are made. What we notice is that the line segment EF, which is obtained by joining the midpoints of the 2 sides of the triangle, is half of the base of the triangle. That is, it is the length of EF is half the length of the third side of the triangle. That is, the length of the line segment joining the midpoints of 2 sides of the triangle is equal to half the length of the third side of the triangle. So EF is half the length of BC, half BC. The second observation that was noticed is that the angle AEF is equal to the angle ABC. AEF is equal to ABC. So in this case, the line EF and BC is cut by the transversal AB, and the angle AEF and ABC are the corresponding angles. When we have 2 lines intersected by a transversal, and if the corresponding angles are equal, it means that those 2 lines are parallel to each other. So the second observation is that the line EF and BC are parallel to each other. So EF is parallel to BC. That means the line segment joining the midpoints of 2 sides of a triangle is parallel to the third side. The first observation is that the line segment joining the midpoints of 2 sides of a triangle is half the length of the third side, and secondly, that line segment joining the midpoints of 2 sides is also parallel to the third side. Okay, so these are the observations that are made with regards to a triangle when we join the midpoints of 2 sides. Okay, now let us formally state the midpoint theorem. What it states is that the line segment joining the midpoints of 2 sides of a triangle is parallel to the third side. So we will prove this by using this construction. So we have our triangle ABC. E is the midpoint of AB and F is the midpoint of AC, and we join E and F to form the line segment. What we have to show is that we have to show that EF is parallel to BC. Okay, and we also have to show that EF is half of BC. We'll do that in the converse part. Okay, so first what we will do is, to make this proof, we will draw another line CD parallel to the line AB. Okay, so we have the triangle ABC. To prove that EF is parallel to BC, we are going to draw a line segment CD parallel to AB, and then we will extend the line EF to the point D, where it intersects with the line CD at the point D. Okay, so we extend EF until D. So now we have these 2 triangles, triangle AEF and the triangle CDF. So we are going to check for the congruence of these 2 triangles and then prove that EF is parallel to BC. Okay, so we look at this construction. What we have done is, we have drawn this line CD parallel to AB and then extended the line EF until it intersects with this line CD at the point D, and then we compare these 2 triangles AEF and the triangle CDF. So what we notice is that in triangle AEF and in triangle CDF, the angle BAC, which is this angle over here, is equal to the angle ACD, because these are alternate angles, because AB and CD are parallel lines cut by the transversal AC, and for these 2 parallel lines cut by the transversal AC, the angle BAC and the angle ACD are alternate angles, so they are equal. So these angles marked in red are equal because they are alternate angles. The next thing is the side of the triangle AF is equal to the side of the angle FC, because F is the midpoint of AC. By our construction, we are joining E and F, which are the midpoints of AB and AC. Since F is the midpoint of AC, AF is equal to FC. And finally, the angle AFE, which is this angle AFE, and the angle CFD are also equal. Let me mark that with a different color. So AFE is this angle over here, and that is equal to the angle CFD, because these are vertically opposite angles for the lines AC and ED intersecting each other. So vertically opposite angles are equal, so AFE is equal to CFD. Okay, so now we have these two triangles to be congruent as per the angle side angle rule. As per ASA, we have one angle, one side, and another angle are equal. So therefore, by ASA, angle side angle, so let me write that down here. By ASA rule, the two triangles, triangle AEF and triangle CDF, are congruent to each other. So once we have these two triangles to be congruent to each other, we can use the CPCT rule by corresponding parts of the congruent triangles. EF is equal to DF. EF becomes equal to DF. So we'll have that ED is basically 2 times EF, which must be the same as BC, right? Because EF is half of BC, therefore ED must be equal to BC. So EF is half of BC and EF is equal to DF, so total ED must be 2 times EF. So 2 times EF is nothing but BC. So the line ED is equal to the line BC, the base of the triangle. Okay, how do we get that? By CPCT, for we get EF is equal to DF. So this line EF is equal to this line DF. So therefore ED becomes equal to BC. Also by CPCT, we get AE is equal to DC. So this line AE is equal to DC. But we also know that AE is equal to BE. Why? Because E is the midpoint of AC. So we get BE equal to DC. So by CPCT, AE, which is this line, is equal to DC, but AE is also equal to BC. So BC and CD are also BE and CD are also equal. That is BE, this line, and CD are also equal. So BE equals CD or DC. Okay. So now what we notice is that we have opposite sides of the quadrilateral BCDE are equal. So we have this quadrilateral BCDE. The opposite sides are equal. That is ED is equal to BC. So these two opposite sides are equal. And also BE is equal to CD. So these opposite sides are also equal. So therefore, a quadrilateral in which opposite sides are equal is a parallelogram. So therefore, we have BCDE to be a parallelogram. And in a parallelogram, the opposite sides are also parallel. So therefore, ED, the side ED is parallel to BC, and the side ED is nothing but the extension of EF. So therefore, EF is parallel to BC, which is what we started off to prove. We had to show that EF is parallel to BC. So we have shown that, first of all, BCDE is a parallelogram. And once we show that it is a parallelogram, we know ED is parallel to BC. So therefore, EF is also parallel to BC. So we have proved that the line segment joining the midpoints of two sides of the triangle is parallel to the third side of the triangle. So EF is parallel to BC. EF is the line segment joining the midpoints of AB and AC respectively. Okay? All right. Now we can state this theorem, theorem's converse statement, and then go on to prove the converse of this theorem as well. So in the theorem, it is stated that the line segment joining the midpoints of the two sides is parallel to the third side. But in the converse, if we say that one of the points is the midpoint and the line segment is parallel, then the intersection with the third side will also be the midpoint of that particular side. That is what is going to be the converse statement of this theorem. So let us state that and then go on to prove that. So in the converse of the theorem, what we state is that the line drawn through the midpoint of one side of the triangle. So the line drawn through the midpoint of one side of the triangle and parallel to the other side will bisect the third side. So we have this line ED passing through the midpoint E of AB, and this line is parallel to BC. Then we have to show that this line will pass through the midpoint of AC as well. Okay, in this, the given is E is the midpoint and the line ED is parallel to BC, and we have to show that F is also the midpoint. In the previous case, the original theorem, E and F are given as midpoints, and we had to show that EF is parallel to BC. In the converse statement, only one point is given as the midpoint and the line is given to be parallel to BC. We have to show that the other point of intersection with the side is also the midpoint of that particular side. Okay, so the converse of the theorem is that the line drawn through the midpoint of one side of a triangle parallel to the second side bisects the third side. So we are given this triangle ABC in which E is a midpoint, F is some point. We are not told that it is the midpoint. Okay, we have to prove that F is some point on AC, and we are given that this line EF is parallel to the base of the triangle, which is parallel to the third side BC, and we have to prove that F is the midpoint of AC. Okay, so to do that, we'll do it in 3 steps. The first step is to make a construction which will help us perform this activity. So the first step is we'll draw this line CM parallel to the line BA. So CM is an extension we have made parallel to BA, and we extend F to intersect the line CM at D. So the line EF has been extended until it intersects with CM at the point D. Okay, now once we have made this construction, we have this quadrilateral EBCD. So in this quadrilateral, we want to prove a few things. So what we will do is we will take this quadrilateral EBCD and then go on to show that this quadrilateral EBCD is a parallelogram. And once we have it as a parallelogram, then we can use the two triangles and prove their congruence, and thereafter we can prove that F is the midpoint of AC. That is what we have to prove. Okay, so first we have constructed this parallelogram by making this line CM parallel to AB first of all, and then extending EF until D. And then in this quadrilateral EBCD, what we notice is ED is parallel to BC because that is given in the theorem. So the line E is passing through the midpoint E and parallel to BC, so that is given. So ED is parallel to BC, therefore EF is also parallel to BC. Okay, that is given. And also this side EB is parallel to DC, because this is by nature of our construction, because we made CM parallel to AB. So therefore EB will be parallel to DC as well. Okay, so we will have EB parallel to DC by nature of the construction. So see, we have ED parallel to BC and EB parallel to DC. So therefore we have this EBCD as a parallelogram. So we have shown that the quadrilateral EBCD is a parallelogram. Now that we have shown EBCD is a parallelogram, we can notice that the opposite sides of the parallelogram are equal. So that means the opposite sides EB must be equal to DC. Okay, so EB and DC are equal. But since E is the midpoint of AB, EB is also equal to AE. So therefore, this AE is equal to DC as well. Okay, so because it's a parallelogram, EB is equal to DC. So we have EB equal to DC, but EB is also equal to AE, therefore AE will also be equal to DC. That's our first observation from this, that AE is equal to DC. Okay, now what we have is EB is parallel to DC. Okay, by construction we have made this CD parallel to AB, right? So therefore EB is parallel to DC, and this line ED is a transversal to those parallel lines. So when we have a transversal passing through two parallel lines, the alternate angles are equal. So for this line segment, EB and DC intersected by the transversal ED, angle AEF and angle CDF are alternate angles. So angle AEF marked by this orange angle here, and the angle CDF marked by this orange angle here, these two are equal. So AEF is equal to CDF, and also angle AFE is equal to angle CFD because they are vertically opposite angles. So now we have in triangle AEF and in triangle CDF, one of the side is equal, that is AE is equal to DC. Okay, then we have two angles are equal, AEF is equal to CDF and AFE is equal to CFD. So we have one side and two angles are equal. So the triangles AEF and triangle CDF are congruent to each other. Triangle AEF is congruent to CDF by the side angle rule, or angle side rule. Okay, SAA or AAS. Either way, you can go from left to right or right to left. If you're going from left to right, it is side angle. If you're going from right to left, it is angle side for this particular case. Okay, so it's SAA or AAS if you're looking at it. Okay, so now we have these two triangles congruent to each other, and once we show that these two triangles are congruent to each other, by CPCT we can state that the side AF of this triangle is equal to the side CF of this particular, of the lower triangle, right? So once we have AF is equal to CF, it means that F is the midpoint of AC. Only then AF will be equal to CF. So therefore we have proved that F is the midpoint of AC. Okay, so the converse of the theorem states, of the midpoint theorem states that the line passing through the midpoint of one side and parallel to the second side bisects the third side. So we have shown that AC is bisected by this line segment which is parallel to BC, and therefore AF is equal to FC. That means F is the midpoint of AC. Okay, we'll stop here. That brings us to the end of the chapter of quadrilaterals, where we have covered all the theorems. What is remaining is just some more examples. So in the next video we'll do a couple more examples related to quadrilaterals, and thereafter we'll move on to the subsequent chapter.